For most of human history, the Earth was not a resource. It was a vault. And like any vault, the difficulty of accessing what was inside was governed by the thickness of the barrier. If you wanted water, salt, or energy from the deep, you had to go down and get it yourself. Human power stopped exactly where the human body stopped. Modern civilization, however, runs on a biological impossibility. The electricity in your home, the heat in your walls, the fuel that moves food across continents, all originate from depths where atmospheric pressure would crush your lungs and ambient temperature would cook your blood. That reality did not appear naturally. It was engineered through a series of physical bypasses. To build the modern world, we had to solve a hard limit. For thousands of years, we could only go as deep as the human body could endure. So we learned how to project human intent while leaving the human body behind. We learned how to dig past our limits. We often talk about progress as if it came from better ideas or greater ambition. It didn't. It came from access, from learning how to reach what the human body was never meant to touch. For thousands of years, digging was a human task in the most literal sense. To reach what was underground, a human being had to go down with it. Wells were carved by hand, using shovels, chisels, and baskets. Workers descended into narrow shafts, where light faded quickly and air grew thin. Every foot of depth meant more earth to remove, more weight overhead, and more pressure from the surrounding ground. Depth was slow, dangerous, often fatal. Walls collapsed without warning. Water flooded workspaces faster than it could be carried out. Air turned foul. The deeper the hole, the harder the earth pushed back. Pain enforced a limit. Energy stayed local. Because bodies could only endure so much, even early attempts to outsmart this limit could not escape it. In the Sichuan Basin of ancient China, engineers developed percussion drilling using long bamboo poles and iron bits. Teams of workers lifted the bit and let it fall, over and over. Iron struck stone. Stone resisted. The tool moved, but the body paid. Every additional foot required time, coordination, and sustained effort. Similar methods appeared elsewhere, including the spring pole systems of early America and Europe, where flexible saplings acted as levers to raise and drop heavy chisels. These techniques allowed slightly greater depths, but the constraint remained the same. Human muscle supplied the force. Human endurance set the ceiling. Depth was still measured in suffering. The real shift came not from intelligence, not from ambition, but from leverage. Instead of entering the earth, humans learned to project force into it. The tool went down. The body stayed out. Spring poles gave way to walking beams. Muscle gave way to steam. In 1859, steam-powered rigs began lifting and dropping thousands of pounds of steel without tiring. The action stayed familiar. A bit struck rock again and again. But the cost changed. The drill moved, even when the human could not. Depth no longer cared about fatigue. For the first time, access was limited by machinery, not biology. This moment is often remembered as the beginning of the oil age. But its deeper significance is mechanical. It marked the point where human endurance stopped being the governing variable. Machines did not need air. They did not feel heat. They did not collapse from exhaustion. They could strike the earth, day and night, layer by layer. They punched through rock that had been sealed for millions of years. But this new reach exposed a new problem. As drilling went deeper, the earth responded differently. Holes collapsed. Walls sloughed inward. Water surged upward. Crushed rock clogged progress. Drilling advanced, then stopped. Again and again. The deeper the hole, the more unstable it became. The earth behaved less like solid ground and more like a pressurized system pushing back against intrusion. The most important challenge was no longer cutting rock. It was keeping the hole alive. Early cable tool wells were empty spaces, filled with air. As depth increased, the pressure from surrounding rock grew immense. Without internal support, collapse became inevitable. When high-pressure gas or oil was encountered, there was nothing to restrain it. The result was the gusher, a violent failure, where internal pressure expelled the drill string and sent oil erupting skyward. These events were romanticized, but they were signs of loss of control. To go further, drilling could no longer be a series of impacts. It had to become a balanced process. That balance arrived with rotary drilling. Instead of lifting and dropping a bit, engineers began to spin it continuously. A rotating drill bit cut through rock, while a column of hollow steel pipe transmitted torque from the surface. But the true breakthrough was not rotation. It was circulation. Specialized drilling fluid, known as mud, was pumped down through the center of the pipe, forced out through the bit, and returned to the surface through the space between the pipe and the well wall. This fluid cooled the bit. It carried crushed rock upward, and most critically, it pressed outward against the walls of the hole. For the first time, the earth was held open while drilling continued. The hole could now exist without collapsing. Depth stopped undoing itself. Drilling no longer required constant pauses to bail debris or rebuild walls. The process became continuous. The rig ceased to be just a tool and became something closer to a life support system for a space that did not want to exist. Pressure inside the hole was balanced against pressure outside. Temperature was regulated. Material was transported efficiently. The earth was no longer being beaten into submission. It was being managed. Once depth became stable, digging stopped stopping. Access became reliable, and reliable access changes everything. Systems expanded. Cities grew. Factories multiplied. Power stopped being local. Entire societies reorganized around the assumption that deep resources would always be available. The distance between effort and outcome widened. Fewer people needed to be near the point of extraction, and the consequences of drilling grew less visible. The final separation came when humans no longer needed to stand directly above what they were trying to reach. Directional drilling allowed boreholes to curve and turn, reaching targets miles away from the surface rig. Down, then sideways, then forward, following a layer through the subsurface like a tunnel you never enter. Offshore rigs floated above nothing solid, extracting from beneath the ocean floor. Geography stopped enforcing proximity. Power could be projected remotely. In the modern era, drilling no longer requires human presence at the site of danger. Machines lift and connect massive steel pipe. Robotics handle hazardous operations. Sensors at the drill bit measure pressure, temperature, and rock properties in real time. Data travels upward through pulses in the drilling fluid, telling operators what the Earth is doing while the hole is still being made. Software predicts failures before a human could sense them. If conditions change suddenly, systems respond in milliseconds. Human operators supervise from control rooms, sometimes hundreds of miles away. Depth responds to commands, not bodies. The final biological limit is gone. By mechanizing depth, we removed a boundary that shaped civilization for millennia. But removing a limit always creates dependence. Every day you turn on a tap, you are trusting a hole you will never see. Every time a city stays warm, every time food arrives on schedule, you are living on the assumption that the vault will keep opening. This is not a moral argument. It is a mechanical one. The Earth is still a vault. We simply learned how to pick the lock without ever going inside.